Okay, welcome to part 2. So, yeah, like I said, they could run the same stats test, examining it from 3 different levels if they wanted more levels, and the stronger the significance level, the lower the chance of making that type 1 error, the better, if you like, their results are, the stronger their significant difference is. If you can say that our IQ test produced a significant difference at a p equals 0.01 level, or p is less than 0.01, that's quite a strong argument. Okay, 0.001 I should have said. Here we go. How do you carry them out? How do you actually conduct the inferential stats test? This is the old school method of doing it. New school I'll talk about in a minute, but this is how you used to do it. Firstly, you've got to choose an appropriate stats test. That is still the same as the new school method of doing it. You've got to choose the correct test. So for the example I was giving about identical versus non-identical twins, that's an independent measures design. So I'd have to use a Mann-Whitney U test. And I'll show you the table of how you can test that, figure that out later. So use the stats test formula to produce a calculated or observed value. So here we go. We take our raw data, we calculate it using that. Thank goodness we've got the new school method. And then it results in what's called a calculated or an observed value. Why is it called that? Because you've calculated it and you observed it in your research. So we've got a U value. Why is it called a U value? Because it's a Mann-Whitney U test. No other reason. We could have called it elephant equals 22. The calculated value of elephant is 22. We're calling it U. It's an observed value. We then need to find the critical value based on the number of participants and the probability level that we have chosen to work with. So critical value, if you want to think about this, is always the same over the years, depending on the number of participants and probability. You're not calculating this. And we're going to compare the calculated value to the critical value. Alright, so what is the critical value? It's like freezing point. Freezing point for water is always 0 degrees. Okay? That is the critical value at which water freezes. Doesn't matter how many times, who does it, who uses the water, where they get the water from, etc., etc. It's always going to be 0 degrees. So critical values don't change. How do you find them? Well, the number of participants is important, the type of hypothesis, whether you've got a 1 or 2, and the probability level you work at. Here's how you find them. You find the critical values in a critical value table. These are in the back of old crusty textbooks, or new, shiny new stats books. This will be a page that has a title of Mann-Whitney U, one-tailed, 0. or p is less than or equal to 0.05. Okay, that's the title that this page would have had. The next page might be Mann-Whitney U, two-tailed, p is less than 0.05. And the next page might have been Mann-Whitney U, one-tailed, p is equal to or less than 0.01. And the next page, two-tailed, p is less than 0.01. So it depends which table, which page you turn to in the book. N1 and N2 refer to our number of participants. So let's say I use 10 firstborn twins, 10 secondborn twins. I see where they meet, and there's my critical value. It doesn't matter if I was working in 1960 or 2016. If I use 10 participants in each of my groups, and I was using a p-value as less than 0.05 and a one-tailed test, that's always going to be 23. Okay. So we've found it. We found our critical value. Nip back. Why do they change, or how do they change? Well, imagine if I just had one set of twins, Dave and Jeff. I've got the same difference in my mean as 100 twins. All right. How does the critical value change? Well, it wouldn't be big enough, first of all. It doesn't accept that you can have one participant in each group. So it says that's a rubbish piece of research. Have at least 6 in one group and 3 in the other, or at least 6 in one and 8 in the other, or whatever. So you see how the critical values are getting lower. It's going to be harder to find a significant difference with fewer participants. Yeah? Because if Dave gets a higher IQ than Jeff, we can't say firstborn twins have significantly higher IQ than second-born twins, because it's just Dave and Jeff who might have had different interests. It's not because they were first and second-born. But if you have a group of 100 youngest and 100 eldest, then if you find a difference, you've got a stronger argument there, because things are ironed out, like experience, environmental experience and things that these two might have differed in. So that's why the critical values get tougher to beat the lower your participants. They're easier to beat the higher your number of participants. Okay, and by beat, what do I mean? We need to be lower. Our calculated or observed value that we worked out from our raw data needs to be lower than the critical value. In this example, it is. 22 is lower than the critical value of 23 from the table. In our results section in our research, therefore, we would write this statement. Due to the observed value of 22 being less than the critical value, 23, and then we give a few details, p is 0.05, n1 equals 10, n2 equals 10. So hopefully you've remembered that's the significance level of the table. The 1 is the number of participants in one group, and n2 is the number of participants in the other group. So we tell the reader where we got that critical value from, essentially. This means the difference between the groups was found to be statistically significant at the p is equal to or less than 0.05 level, allowing the researcher to reject the null and accept the alternate hypothesis, which was, and you restate your accepted hypothesis. Okay, but you see how it's harder to get. We go back to the table. If you've got a very small, if you've got a very small sample, it's harder to get a calculated value of less than 6. It takes an awful lot of a very big significant difference to get the observed value of less than 6 there. So the higher your participants, the higher your critical value is. So it's kind of easier to get the observed value. New school way. You take the raw data, you put it into a stats test, online a lot of the time, but there's a program called SPSS, and it tells you the exact level, the point at which it is significant, like p equals 0.0456. And you can then tell, right, it's less than 0.05, so we're going to accept our experimental hypothesis, alternate hypothesis, and reject our null. Okay, so it tells you exactly what level it is significant at, and you can then judge from that. The program will actually tell you outright, this is significant at a p is less than 0.05 level, but it will give you nowadays the actual value that it's significant at, the tipping point, if you like, at which the bridge would collapse. Okay, so that's your exact error, you've got a 4.5% chance of error in your findings, but because that's less than 5%, you'd accept your alternate. If that came out as p equals 0.06, you would accept your null and reject your experimental, because it's lower, it's higher than the p equals 0.05 that psychologists agree with. Okay, so much easier the new school way of doing it, but you still need to know which stats test to use. How do you work them out? On the A-level spec, you need to know which non-parametric test to use. You're not going to be asked for anything other than these 4. Okay, so you need to justify which stats test you would use. I should have said these 5. Easy for a correlation. If you're looking for a relationship, your justifications in the exam, when it says which stats test would be most appropriate for this scenario, you go, well, it's exploring a relationship between 2 variables, and it's using ordinal data, or it's using interval data. Check, remind yourself what those 2 are if you're not sure. And therefore, I would use Spearman's rho, or Spearman's rank correlation coefficient. And that would get you the marks. For these ones, for the experimental ones, why are they experimental? Because we're looking for a difference between two conditions. So, exploring differences, if you have ordinal or interval level data with an independent measures design, it's a Mann-Whitney U-test. The way I remember it is Whitney Houston was the original independent woman. The Wilcoxon-signed ranks test is for a repeated measures design with ordinal or interval level data. And for the nominal level data, independent measures, you get a chi-square, which looks like that because you've got independent measures. You've got categories is nominal data. 3, 5, 8, 9, male, female, wearing their seatbelts, not wearing their seatbelts at a stop sign. Okay, the chi-square literally looks like a square because they're number of categories, categorical data. And for your repeated measures, the binomial sign test. How do I remember that? Sign plus negative. Okay, how do you get categories for that? Well, think of this as an example. Categories in a repeated measures design before therapy. Let's say we're comparing mood before therapy to after therapy. And for each participant, for participant number 1, has their mood increased after therapy? Yes, and it gets a plus. Has this number 2? They've gone down. Number 3, they've gone down. Number 4, they've gone down. Number 5, they've gone up. We have got 2 people who have improved after therapy and 3 people who have decreased after therapy. Okay, that's not ordinal data. Ordinal data is where you would rank them from the top in terms of their mood to the bottom in terms of their mood. We're not doing that. We just want to know, does this therapy work or not? So it's categories, work, not. But it's repeated measures because we're measuring before the therapy and the same participant is being measured after the therapy. So it's a binomial sign test. So if you can remember that example with the positive and the negative, then repeated measures, you remember that it's repeated measures because it's before and after the therapy. And if you can remember this one, just looking at a stop sign, at some traffic lights, counting the number of males who've got the seatbelt on or not got the seatbelt on, then they're not going to come round again and be repeated as a female. They're around the same thing. You're just going to be doing an independent measures design, categories. Okay, so try and remember those. Those are the only ones you need to know. But these are where you get the marks. Justify which stats test. Number 1 mark, we're looking for a difference. Number 2 marks, the data was ordinal. Number 3 marks, an independent measures design. Therefore, 4 marks, I'm going to use a Mann-Whitney U-test. Okay. You only need to know the criteria for a parametric. Parametric tests are essentially really strict scientific tests. We rarely use them in psychology because we don't often produce highly scientific tests. So parametric tests, you just need to know these 3. What's the conditions? Standard deviation is not significantly different. Data is normally distributed and data needs to be interval or ratio. You don't need to know why, you don't need to know how, just know those 3 justifications. Okay. Standard deviation's essentially normal, data is normally distributed, and data has to be interval or ratio. Okay, now that stuff about the calculated value, does the observed value from your stats test have to be higher or lower than the critical value? That's what I've used these for. For these ones, the ice cream means the observed value has to be lower than your critical value. For the chi-square and the Spearman's rho, it's the opposite, it has to be higher. Because remember, your Spearman's runs from a -1 to a +1, so the stronger your critical value is going to be down here somewhere. It's got to be up there somewhere. Now, just learn those. Just learn that that's got to be low. The observed value's got to be lower for those. It's got to be higher for those. Pause this video on these. Those are a bunch of examples of where I've said whether you would accept or reject your nulls. Okay, pause that and have a go at it. Summary. Stats tests look for a calculated, compare it to a critical. Anything equal to or below 0.05 is classed as significant, anything above, not significant. Thanks for listening.